next learning objective is about geodesy and how it is used to model the surface of the Earth and develop various datums. And the science of geodesy is basically the science of measuring the shape of the Earth. We need to know the accurate shape of the Earth so we can accurately determine locations of the surface of the Earth, coordinates. We can accurately create maps, charts in the atlas. And our understanding of the shape of the Earth has evolved over time. It, you should be, you should see how some of the old models were may sound ridiculous in the modern times, but they were believed to be true at one point in history. But let's talk about more recent models. The first one is the spherical model, and then ellipsoidal model. In both of these cases, the thing that has also evolved along the way is the size of the Earth. Now, the oldest understanding of the size of the Earth was done by Eratosthenes, just a few hundred years before Christ, and he was able to measure the circumference of the Earth pretty accurately, 40,250 kilometers. This was an experiment done in Egypt, in Alexandria and another town close by. And you should read the corresponding text in the book to learn how this measurement was done. And later on, this was improved by Posidonius, but it was an underestimate, 38,400 kilometers. And there was another estimate of 28,960 kilometers, which was significantly underestimated, but unfortunately used by Ptolemy to make his world map, which was used until the 1500s. So it got carried over for many hundreds of years, an inaccurate map. It wasn't until Sir Isaac Newton that we start the idea of the spheroidal Earth, which is basically a sphere with a flattening. So if we are looking at the cross sections here, we have a cross section of sphere is a circle, but if we flatten it from the top and the bottom, we get an ellipse shape. And Sir Isaac Newton was able to reason that there are rotational forces that would make the Earth a little bit flatter than it looks like, or it seems to be. So with the size of the Earth in question, our modern Earth is a spheroid modeled as an ellipse with a semi-major axis, which is different from its semi-minor axis, and its average radius, which is basically the average of these two numbers, where semi-major axis is used twice, is 6,371 kilometers approximately. So we know that we have a reasonable idea about the size of the Earth. And when we talk about the shape of the Earth, then again, we have treated it as a sphere and more recently as an ellipsoid. By the way, another name of ellipsoid is oblate spheroid. So if we were looking at it as a three-dimensional space, then its horizontal semi-major axes along x and say z direction are both A, and along y direction is B. In this case, I'm treating this as y direction. And so if and in case of sphere, A is equal to B, and in case of ellipsoid, A is greater than B. And there's a measure called flattening, which determines what is the relationship between A and B, and this flattening tells us how has this sphere ellipsoid been pushed down a little bit. And if we look at this from the point of view of the flattening, then it's a pretty small number. It's usually expressed as 1 over something. And the flattening of a sphere will be 0 as A is equal to B. Now I want to point out at this point that both of these, a sphere and ellipsoid, are just models. And as we talked about in the second module, that models are not accurate, but they represent the reality in certain ways. So these two shapes are representations of the Earth, but they are not the true shape of the Earth. The true shape of the Earth has some differences that are not modeled by either of these two models. So moving on to the idea that we have the ellipsoids, but how do we determine what ellipsoid to fit into the Earth? And for that, we have geodetic surveys. We conduct surveys, we measure a lot of points on the surface of the Earth, and then we try to fit a surface that best represents those points that we have measured. You may know from your surveying class, when you do surveys, you have these benchmarks. And benchmarks are fixed points with known coordinates and known measurements. And these points are used to find out what is the best ellipsoid that will fit those points. And that is the ellipsoid that we use. Now, many countries and continents, based on their size and their scale, have their own surveys, and so they end up fitting their own ellipsoid. And this way, we end up with having many ellipsoids that are best suitable for different parts of the world. For example, if ellipsoid 1 is suitable for one part of the Earth, it may not be suitable everywhere, and we may need another ellipsoid, ellipsoid 2 in this case, to model the Earth if we were in a different part of the Earth. And so if we look at this table, this is from your book, you can see that various users have different ellipsoids, and each ellipsoid is described by when was it created, what is its semi-major axis, the radius A, then what is its semi-minor axis, the radius B, and then the flattening factor, which is A minus B over B. And as you can see, it is different for different parts of the world, and it best suits that region. The geodetic survey points are best fitted into this particular ellipsoid relevant to each region. So with that idea, the question arises, what is the true shape of the Earth? And we probably will never be able to model it exactly. The only way to actually have it is exactly mapped, which is also not very easy to do. So the another idea that comes about the shape of the Earth is the idea of geoid. Now, a geoid is basically the mapping of the gravitational field of the Earth. If we look at the density of the Earth, we know that it's not the same everywhere. The density of the Earth inside, the matter inside the Earth changes from place to place, which means at some parts the Earth is dense, whereas the other parts it may not be that dense. And wherever there is denser mass, there will be higher gravitational attraction. Wherever there is a rare mass, there will be lesser gravitational. So we expect the gravitational field around the Earth to be dependent upon the distribution of mass inside the Earth. And that's the idea behind geoid. A geoid is a 3D surface along which the pull of gravity is a specified constant. So if we look at this cross section, the actual surface is the green line, and let's say we have the mean C surface, which kind of represents a surface that has been used for a long time as a reference for measuring heights. And then we have some measured locations through geodetic survey, and we fit an ellipsoid into it. A geoid is a line over which our plumb line will always be pointing vertically down. Now, in general, it will match the sea level surface, because the surface of the water is going to um, contour itself to match with geoid. But of course, it is not the mean sea level because the level of sea might be different in different parts of the world. But if there is a mean sea level um, at that particular level of G, then it will match the geoid. So what would a geoid look like? Well, here is the mapping of a geoid, and it is nothing that we have so far modeled. Neither a sphere or ellipsoid. It is pretty wrinkly surface, and but that's how the gravitational field of the Earth, an equipotential surface of the gravitational field, looks like. And this is another way of modeling the shape of the Earth. Is basically relating it to the density of the matter in the Earth. So with that shape of the Earth also taken into consideration, the next question arises: how can we use it as our reference? So we use the ellipsoid as the geodetic datum. A datum is a reference point, line, or a surface that can be used to measure other points from it, or other lines or other surfaces. So it's a plural for the word data. A geodetic datum is a reference surface used to locate points on the surface of the Earth. So in our case, we fit an ellipsoid, and we assume that it best fits the ground surface, and it matches the benchmark points that we have measured through surveys. Now, typically, an ellipsoid that is used as a datum is described by 8 parameters. So 2 of the parameters are the size of the ellipsoid, which is A and B, the semi-major axis and semi-minor axis. Then there are 3 other parameters called X, Y, Z. This tells where is the ellipsoid, where is the origin of the ellipsoid. And then there are 3 more parameters, alpha, beta, and gamma, that tell us the orientation of the ellipsoid. And with these 8 parameters, we can exactly specify what is the ellipsoid that best fits, and we use it as our reference surface. Now, this might be good for today, but in a couple of decades, it may become outdated. We keep getting new surveys, and nowadays we have a lot of GPS data coming, so a lot more observational data is available, and we continue to adjust our datum to improve the accuracy of the locations on the face of the Earth. So um, here is a couple of different datums that we have used previously, and how they have. This is just a cross section, but you can see the origin is different in the 2 datums, and it keeps changing as we get our better understanding of the size and shape of the Earth. So the geodetic datum has 2 pieces. One is the horizontal datum, and horizontal datum is set by choosing the ellipsoid. And this is the ellipsoid on which we overlay our coordinates, and then those coordinates are basically longitude and latitude are used to locate all the other points on the surface of the Earth. Some of the commonly used datums are, in America we use North American datum, or NAD. They are the oldest one is 1927, but there is 1987, and so on and so forth. We have World Geodetic Survey, WGS. In here we have 1984 and onwards. Then we have ITRS. This is International Terrestrial Reference Frame, that was started in 1988, and there have been some versions of that too. And it is becoming quite popular, and it probably will become the world standard in future. So if we look at the horizontal datum, you can think of it as that if we have the red line as our real Earth surface, and the blue line as the ellipsoid that we have fit into it, then if we are interested in knowing the location of this point on the red, then this blue surface is acting as our coordinate system. and whatever is its projection on that coordinate system, that is the longitude and latitude of that red point. And that's how that's the purpose of our horizontal datum, is to help us locate points on the real surface of the Earth. Similarly, we have the vertical datum. Now, vertical datum used to be mean sea level. So all the heights, even now you see our heights are measured from mean sea level. But in GIS, the new vertical datum that is appearing is the geoid itself. And it is related to our previous knowledge that was above ellipse or above the geoid. So the surface of the Earth and the height above the ellipsoid have a distance called ellipsoidal height. And if we are looking at the geode height over the ellipsoidal surface, that's called the geoidal height. And the orthometric height is what's the new height that we consider height above the geoid. And when we start using the geoid as the reference surface for our vertical data. Anyways, when we are dealing with digital elevation models and maps that deal with the surface of the Earth and its height, vertical datum is considered. But we still see a lot of data that is coming as height from mean sea level, which I explained is a lot of times related to geoid, but it may not be the geoid. So as I mentioned earlier, whether we have horizontal datum or vertical datum, they keep getting adjusted because of more observational data that we keep receiving. Nowadays, with the GPS satellite data coming on a continuous basis, we have a system called continuously operating reference system. These are beacons around the country that continuously broadcast the location of their own station in a very accurate way. And so all the other stations around the country can update their measurements based upon what they receive from these stations. And so this kind of observational data can be used to improve our estimate of the datum. Here's an example. Let's say that long time ago we had point 1 and point 2, and we fit ellipse A or ellipsoid A to model the surface of the Earth. And over time we developed some more observations, 3, 4, 5, 6, and 7, and we can improve our estimate of ellipsoid by taking into consideration these points. And you can see that in general the error has reduced by our better understanding of the ellipsoid, or basically we have adjusted the datum by adjusting the ellipsoid. And what ends up happening when we do these adjustments, the actual coordinates of the points on the surface also change. So here is an example from your book where the datum shifts resulted in the coordinates shift. And here is a point, it's a Bloom 1 point in New Jersey. And when it was under North American Datum 27, it had these coordinates. And then when this datum was updated or adjusted in 1983, it moved by 36.3 meters, which is a significant shift. And then later on, as I mentioned earlier, I think I missed this high accuracy reference network. This is a private survey that is also used to improve accuracy. So later on, HARN was used, and there was a minor shift. Then CORE's system again made a minor shift. So this is not that the point Bloom 1 on the surface of Earth is moving, of course, obviously. It's the coordinates of that point are getting improved as we improve our datum with more measurements, observational measurements. And lastly, I want to talk about datum transformation. So once we have a datum and we develop our maps, and after a couple of years we have a new datum. Now if you pick up an old map and you know that it was prepared using an old datum, there's a need that you need to match the two maps, the present map and the past map. And for that purpose, we need to update the datum of the older maps to match the datum of the present map. And for that purpose, we have to go through a process. First of all, we convert the source or the old datum, um, the geographic coordinates to its Cartesian coordinates, which is basically taking longitude, latitude, and converting them into XYZ, 3D XYZ values. And then we shift these coordinates based upon our new ellipsoid. So this is a real point in space. Now I can shift, which means the new ellipsoid may be shifted a little bit. It may be bigger or smaller. It may have different A or B values, so I scale it. Then it may have a different angle, alpha, beta, gamma, so I rotate it. And by doing these three steps, I have taken this point and I moved it onto the new ellipsoid that is shifted, scaled, and rotated. And then once I have those new x prime, y prime, and z prime coordinates, I convert them back into geographic coordinates, lambda prime and phi prime. So basically I have taken lambda phi in one datum and brought them into lambda prime and phi prime of the new datum. And this is how we can do datum transformation.